Hello, everybody. Welcome to this webinar organized by the Office of the CTO at GitHub. Today, it's my pleasure to introduce Simon Peyton Jones. If you have touched functional programming, you will already know of Simon. He is one of the primary contributors to the design of the Haskell programming language and the lead implementer of the glorious Glasgow Haskell compiler, GHC. His work is characterized by taking deep theoretical insights, applying them to amazing practical benefit, and then explaining it all with disarming clarity and delight. Originally, due to my own personal tastes, I wanted to talk to him about his research and delight us with yet another nugget of theory brought to life in GHC. But today, he is in fact talking about a different but equally important topic: teaching computing to the next generation. Simon chairs the Computing at School CAS group, an organization which aims to promote the teaching of computer science at school. Following these efforts, in 2019, he was appointed chair of the newly founded UK National Centre for Computing Education. Before Simon kicks off, a few housekeeping remarks. If you have a question at any time during the talk, please use the Q&A feature of the GoToWebinar app to post these. Throughout, we will be watching these questions. If possible, Simon will answer them live immediately, or we'll collect them and address them at the end. So with that, Simon, over to you.
Great, thanks, Ugo. What a delight to be with you all. Thank you for getting up. It's 9 o'clock in the morning for many of you. So bright and early for you, afternoon for me. Ugo described this topic as equally important as Haskell and functional programming, but in some ways I think it's even more important. So with functional programming, I hope to reach millions of programmers. With education, we want to reach every child in the country and actually every child on the planet in due course. So it is really, really important. Here is the a quick picture about where we're starting. What I'd like to do is to take you on a journey. This is a personal journey for me. It's been a journey for the country that I live in, the United Kingdom. And I'd like to encourage you to think it could be a journey for you and your country as well, and talk a little bit about how you might get involved in this. So here's how it started for me. It was around our kitchen table in around 2007, when these are my 3 children. We were talking about their school, what happens at school, and they were describing computing as a school subject that they were doing. It was then called Information and Communication Technology. And to my dismay, they described it in terms of contempt. They regarded it as being completely beneath them. It was about how to use Word and PowerPoint and Excel and very little else. So I found that I couldn't draw a connection between the subject that they were learning at school and the subject to which I had devoted my professional life, because I thought it was so interesting. They went sort of like this. Whereas in biology or natural science, I think the kind of stuff you learn at school is related to the stuff a professional biologist or natural scientist might be involved in. So that felt very different. So talking to others, we ended up starting a group called Computing at School. This is back in 2007. This was a sort of guerrilla volunteer group, grassroots, bottom up, unfunded, no organizational structure, nothing. But our idea was, let's try to do something about the computing education that our children are getting. So it's now very much bigger and has proved to be quite an influential group. And I have the honor to serve as its chair still. So the first thing we wanted to do in CAS was to try to say, what is it that we want? It's not enough to criticize what other people have. We have to say what we want, what we think should be the case. So here is our vision. Every child should learn computer science as a foundational discipline in the same way they do maths and natural science, and that means from primary school onwards. So you'll notice this is a big shift. The information and communication technology, as the subject as then was quite vocational in its focus. It was oriented around technology and skills with a strong emphasis on, this is a useful thing to do. Whereas with natural science, we get all children to learn a bit of physics at an elementary level, a bit of chemistry, not because they're going to become physicists or chemists, all of them, a minority will, but only a small minority. We teach them this because we think it's important to learn something about the natural world that surrounds you so that you can become an informed agent in it, have agency in the world. And it's the same with computing. If we understand something about all this sleek technology that surrounds us, we'll be better equipped as citizens, and a minority will go on to be well equipped for good jobs. So there's a lot of things to unpack here. It's about ideas and not primarily about technology. From primary school onwards is important because this is saying it's for everybody. And when it's saying it's for everybody, it's not just for future software developers, it's for future brain surgeons and future plumbers, future everybody. That it's a subject discipline, not just a skill. We'll talk a little bit more about that. And its goal is to turn our children into informed critics or authors of computational and technological stuff rather than mere passive consumers of it. I hope that makes sense as a way to frame it. So that was a very big shift from what we had before. So in talking about that, we have to say something about what do we mean by computer science anyway? So computer science is well established as a university level subject, but it was not really at all well established as a school subject. But if you say, when we think about natural science, we think about it as a subject discipline. What is the subject discipline that underlies all this technology? Well, it's computer science. What is that? So this is a way that I found I ended up explaining it, that it's the study of information, computation, and communication in both natural and artificial systems. Artificial systems being computers, but natural systems just being like the world that surrounds us. But notice this is not technologically oriented. It's they're sort of ION words rather than databases, computers, and networks, which you might think of as being the technological bits of information, computation, and communication. So here's a little video that gives you an idea of what we have in mind. I show this video often, even to everybody, everybody from politicians to technology people, because it's helpful in explaining what we're about. So this is children doing sorting in a sorting network drawn on a school on a floor. They're primary school children. When two children meet at a box, they swap places if one number is bigger than the other, and they don't swap otherwise. And so this is a sorting network, and if they follow the rules, then when they get to the end, look, they come out sorted. And you can do this kind of thing in an experiential way. You can do it with bigger numbers, you can do it with a bigger network, you can do it as a competition. Here's some children doing it on a school playground, 40 of them. Tim Bell, who made this video, told me that it took them the entire morning to film that last 10 seconds of video. So take another look at it another time. But I love this because there are no computers in sight. There's no technology here at all. And yet, there's something very interesting and intriguing going on, something computational and perhaps surprising that this network drawn on the floor can sort. And moreover, it allows a sort of experiential approach. It means that children can say, oh, well, maybe the teacher put us in a particular order at the beginning so that we would come out sorting. Let's see if we can fool the teacher by putting ourselves in a different order at the beginning. And they follow the rules and they're still sorted. And then they might say, I wonder if every input combination will lead to a sorted output. And that's, of course, a much harder question. But I love the way that a primary school child could at least ask that question. And they could say, could we do the same thing with a different arrangement of boxes of wires or fewer boxes and wires? And how would we do it on a larger set of inputs? And all of these things are amenable to practical experimentation, not just the theoretical reasoning. And once again, no technology in sight. So I like that very much. And so that's kind of like the idea. Ideas, not technology. So here's another example about the way in which we're trying to decouple computing from the idea of people sitting in darkened basements with glowing screens. It's really an interdisciplinary subject. Here's a little diagram that helps you generate English language sentences. So the rules are you just put your finger on the dots and follow the arrows and say the words. You could say, the old clown sang, and going backwards, a tiny pirate laughed, and then you can leave. So it's not long after you show this to children that they start writing diagrams of their own to generate more sentences, usually rude ones. And in fact, after a bit, they start retrospectively reinventing the laws of English grammar, if you like, insofar as there are any such laws. But you and I can look at this and we can think it's just a finite state automaton. We could use it to describe a microwave oven. And indeed it is. It's a sort of computational idea that's usable in all sorts of places, but you can make it surface in a way that somehow relates to other school subjects. That's very good when you're at primary school, when we don't have the kind of very siloed effect that we get in university or secondary schools. Primary schools really have one teacher for a class and they teach sort of subjects kind of smushed together. So very good for that. So that's just a quick, very, very quick sort of glimpse about what computing or computer science as a school subject might look rather different to the way we think about it as a university subject. I think it's also helpful just to sort of debunk some myths. Partly I'm telling you this is a way you can have conversations with other people about what we're trying to do. In some ways, I think you'll say, oh yes, I understand all this. Of course, how could we do anything else? But being able to explain it is important. So myth one is that computer science is all about computers, and it really isn't. There's this famous quote from Dijkstra that computer science is no more about computers than astronomy is about telescopes. I like that quote. It's not quite as apposite for computer science as astronomy, but close. And I've shown you this sort of unplugged approach in the to teaching computing in that little video. And I think also we can reach beyond technology in a different way by looking at the natural world and say, well, an ant colony has lots of little computers, that's the individual ants, running very simple programs, because an ant brain is not very big, but somehow collectively they do something that is greater than what one ant could do, and they somehow cooperate, even though they're running quite a small program. That's a very strange and remarkable thing to happen, but it's a computational and informational and communicational phenomenon. Second myth is that if you ask the man in the street, should we teach computing at school? They'd say, oh, maybe yes, we should teach every child to code, and we should, but it's not all about coding, right? It's a very popular meme, but I want to keep us in a bigger frame, if you like. So I think of programming is to computer science in the same way that lab work is to physics. Right? We would never, if we wanted to teach a child physics, we wouldn't just put them in a lab together with stopwatch and inclined planes and ball bearings and expect them to reinvent Newton's laws of motion. We would definitely want them to do lab work because that's what brings physics alive, right? But we wouldn't. We teach them some principles as well. So programming is incredibly important. It's crucial. It's motivating. Everything in computer science is shot through with programming, but it isn't the subject, right? It can be seductive and even distracting as we get sort of addicted to programming and forget about the principles. So I'm a little bit worried that in 10 years' time, our Secretary of State for Education will say the reform of the English national curriculum has been a great success. All children leave school knowing how to program in Python. Right? That would not be a good outcome. So, third myth. Often when you start talking about this, people will say, but computer science is not really for creative people, is it? Creative people. But I love this quote from Fred Brooks, who said, the programmer, like the poet, works only slightly removed from pure thought stuff. She builds her castles in the air from air, creating by exertion of the imagination. Few media of creation are so flexible, so easy to polish and rework, so readily capable of realizing grand conceptual structures. That's a lovely quote. Fred Brooks was almost a poet himself, I think. So programming itself is intensely creative. Every program is a new thing, something nobody's done before. And in fact, the medium of our creation is so powerful and so flexible. Really, the main thing that limits is our own inability to grapple with complexity. If you build a skyscraper out of steel, there comes to a point where if you build it any higher, it just falls down, but steel isn't strong enough. That's not really true of software. It's our own inadequacies that stop us building bigger programs. That's quite a challenge. So I really like this this Berkeley-based computer science course called The Beauty and Joy of Computing, because I think it puts the emphasis in the right place. Fourth thing, that a good computing education is all about good jobs, particularly geeky jobs. I don't think so. I think it's mainly about understanding the world and being equipped for life more generally. It will equip you for geeky jobs as well, but it'll also equip you for jobs in completely different subjects and just for being an empowered citizen. So, and the other thing to remember is there's always a danger that we'll train people for today's jobs, not for tomorrow's jobs. So that's the stuff about teaching people subject disciplines is that that's stuff that doesn't date quickly. It lasts a long time. It's useful as successive waves of technology roll through. That's our ambition. It's not to teach children about one wave of technology, but about give them the intellectual scaffolding and toolbox that will enable them to grapple with successive waves. So I think of the picture like this, that there's a sort of two pillars to this. There's the educational drive, which says computer science is a foundational subject discipline that every child should learn because it'll equip them for life. But also there's a more instrumental pillar, which is that it's a subject that will equip our children for jobs of the future, actually not just computer science jobs, but lots and lots of different kinds of jobs. And these two pillars solidly underpin computer science as a school subject. So that was the vision that we articulated. But it's easy when you sort of talk with these big pictures to get to lose track of the what happens on the ground. I just want to give you a little encouraging vignette of something that happened. This was now about 5 years ago, I think, this particular occasion, in which this is Miles Berry, who's a UK educational computing educational person, who gave a workshop in London in which he was teaching some children about Scratch. There were primary school children, in fact, and this girl, Em, realized that she could replace the repeated steps of this little turtle program to draw a square with a little for loop. Nobody taught her about for loops. She just saw that in the palette of things she could do. And she did a bit of guessing and some experimenting. Notice how experimental all of this is, right? And she was able to write a for loop that did the same thing. And then she was so pleased about this, she told her colleagues in the little group that she was in. And that gave quite a boost to her self-confidence. And this is what her teacher wrote to Miles some weeks later. Here I have Em, self-esteem going through the roof, and she has associated this computing success with maths. Over the last couple of weeks, she's solved maths problem after problem, met target after target. She's truly flying. She is going great because of a positive experience in a computing workshop in London. And I love this because I find it quite touching, actually, because I feel this is what it's all about. This is about giving our children, perhaps quite young children, a sense of self-worth and self-efficacy and agency and ability to do things that perhaps some of them had not felt before. And this is going to be more pronounced for some children than others, but for some it will be really quite pronounced. I think probably for many people listening to this talk, I hope that computing has been a way to change the world, to be a personal vocation. Okay, so back to the UK journey then. So we kind sort of articulated this. Then we got lucky that there was a reform of the entire national curriculum in England. So at that moment, the Department for Education was kind of up for input about what education in all subjects should look like, and we were able to say, well, this is what we think computing education should be like. The Royal Society, founded by Isaac Newton, it's sort of big noise scientific society in England, and the important thing is it's one that the government listens to. They published a very influential report in 2012 called Shut Down or Restart, the case for computing education in school. It's readily available, just Google on that title. Then there was a working group to write a new curriculum. And in the end, the Department for Education outsourced writing the new curriculum to a working group, which I was lucky enough to chair. And the new curriculum was published and launched in 2014. So here, in fact, is this new curriculum. The constraint was, they said, well, you can say what you like, Simon, but it all has to fit on 2 sides of A4. So here is the beginning of the 2 sides of A4, and this is the national curriculum in England for computing. And it says every child, this is from 6 through to 16, should be able to understand and apply the fundamental principles and concepts of computer science, should be able to analyze problems in computational terms, and have repeated experience of writing programs to solve such problems. This is in black and white in the UK's national curriculum. I'm very proud of this because I think it's very unequivocal about our aspiration, what we're trying to do. Okay, but we haven't lost track of using, so it's important as well as being computers to be able to use computers confidently and competently, and those are the last 2 bullets you'll see on this slide. Okay, nobody has typed in. I'm looking at the questions panel and not a single one, so don't just sit there. Think about what's going on here. So backing up then, New 2014. So what happened to a new curriculum? It's only 2 sides of A4. How do we turn that into reality? Well, there was a lot of paddling under the water. And then the Royal Society produced another report in 2017, and in response to that report, the government recognised that they needed to offer some training to teachers, because of course teachers were not trained to teach computer science. They just weren't. Very, very few of them had computer science degrees, and computer science as a school subject was entirely new as a school subject. So that was so the government then agreed to fund the National Centre for Computing Education, which I'll say a little bit more about in a sec. So here it is. What is the National Centre? It's an £80 million 4-year programme starting about 2019 to train and support teachers to teach computing. So computing is meant to embrace both computer science and the more applied aspects as a school subject from in primary school and secondary school. Across, in every school, in every part of the land. And there are a lot of schools. So we're talking about 3,500 secondary schools, 16,000 primary schools, and 6 million children. That's a lot. So the National Centre is it's a huge enterprise, and it's doing a ton of stuff. I'm not going to tell you in great detail what all that stuff is, because there's other things to get to as well. But it's I serve as its non-executive chair. Still, my day job is still functional programming and research at Microsoft in this and machine learning. But I have a sort of night job, as it were, which is being chair of the NCC, which I love. So just to pause for a moment and take stock, what's happened? So it really is amazing that in only 10 years, it's quite a long time, but still, now I'm 60, I realize that 10 years is quite short, actually, in educational terms. We've articulated a new vision of what a good computing education might like. We've built a community of practice, a grassroots community of teachers who are, collectively more and more buying into this vision. We got established in national legislation, actually, a new policy that embodied that vision. That really establishes a completely new school subject, namely computer science, which was firmly established at university, but not at all at school. And we got the National Centre for Computing Education established as a professional development program. So you will know that if you ever go hill climbing, that whenever you walk up a hill or climb a mountain, when you get to the top of it, what do you see? You see bigger mountains behind. So turning all this aspiration and joy into an actual vibrant reality in every classroom is not easy, right? There are a lot of classrooms, there are a lot of teachers. And even £80 million, which sounds like a lot of money, isn't all that much. If you divide it by the number of schools and the time, it's only £1,000 per school per year, enough to buy, a couple of laptops. So it is not a lot of money. But it is hugely more than zero, and we can do a lot with it. So I've had cause over the last 10 years to talk to a lot of teachers, and my respect for them as a profession goes up every time I do so. Teachers are actually amazing. Being a teacher is pretty hard. You get pulled in all sorts of directions, and being a computing teacher is actually quite a bit harder, particularly in computing because it's in so much flux. Essentially, we're introducing a massive step change into the subject that they teach, and we're asking them to, as it were, change the wheels on the bus while the bus is still going along. They can't say, no school for 2 years, we're going to figure this out. The children are arriving in September. Computing is a very young subject, right? We have centuries of experience about how to teach maths at school, but we have a few years experience only about how to teach computing at school or computer science at school. So just how do you do it best? That's quite hard. We don't know, and that's hard for teachers. Qualifications are changing, and there's a big shortage of teachers as well. So as one teacher put it when she was talking to me about this, she said, in my school, it's me, or me. And I felt that sort of sense of kind of not exactly loneliness, but the sense of not. She clearly didn't feel she was living in a system with a web of support, and that's what I hope the NCC and CAS will help to do. There's a question. Thank you, William. But a question about abstraction. I think I will come to that at the end. But yes. Yes, I'll come to that at the end. Good, thank you. Keep asking. So I want to give you the sense of a lot has happened, and it's very exciting, but huge challenges still to turn it into reality. So the question I then want to ask all of us as computing professionals is, well, how can we help? And And I want to answer that in two ways. I want to describe to you a particular project that I'm involved in here at Microsoft, which I'm enjoying a lot, and then zoom out a bit and talk about what else might we do. So here's the particular project that I'm involved in at Microsoft called Project Quantum. So here's the question: how can we help teachers in a tangible, concrete, actionable, but scalable way, one that will work across lots of teachers? So one particular thought is this: all teachers need to track the progress their students make. And if they've got a few dozen students, they can do that kind of by the seat of their pants. When they've got a few hundred, as many teachers have across a big school, they are going to need to be somewhat more systematic about it. So what they do is they inevitably produce tests or quizzes. And where do they get those tests or quizzes from? Well, mostly they write them themselves. And that's absurd, right? It's incredibly duplicative because they're writing them themselves. Also, writing good quizzes is hard. Writing good questions is a difficult skill. And it's particularly difficult if you're not an expert in the subject, which our teachers are largely not. So an obvious suggestion would be to offer a corpus of high quality questions that teachers could then draw on to save them time, but also give them access to high quality questions. So the way that's typically done is by paying experts to write questions and then field trialing those questions to find out which ones work well. And that's quite expensive and tends to lead to a smallish corpus of questions when it's almost irresistible to then monetize that in some way. That's not what we really want here. So another possibility, which I was talking to some assessment experts and they'd begun to think about this already, is to crowdsource the questions. So maybe we could build, this is in the spirit of an open source software. Instead of closed source software, we'll pay somebody to write it and then it's ours. We'll use open source, in this case, open source questions. We'll get anybody to write questions and contribute them and share all the questions that other people have written. So, and not only that, but we'll share all the data from the answers that students give to them in an anonymized form to educational researchers anywhere. So if this worked, this would be not just the UK, the same corpus could work anywhere in the world, and not just computer science, the same approach might work in any subject. So that's quite an exciting possibility. Just one thing, this is all about low stakes formative assessment. This is sort of technical term in edu-speak term. Summative assessment means weighing the pig. At the end of the course, did you pass, right? Are you, are you fat enough, right? Have you got to the bar that means you've passed the course? That's summative assessment. Formative assessment is about, is more like going to the gym than going to the Olympics. It's how you get strong. Right, so you're going to do questions in a sort of quiz kind of way, perhaps every week, because then you'll learn about what misconceptions you hold, what things you can do, what things you can't do. You'll learn what to study, and actually the act of doing questions can itself be very educative. So formative assessment is what all this is about, low stakes. Right, so then the last part of this puzzle is we met up with a partner called Eedi, who they're actually a small British startup who already had a very large corpus of maths questions. And they already had a platform to distribute it on, because it's no good having a corpus of questions if you can't put it in front of a lot of teachers and a lot of students. They already had a platform, they already had a corpus of questions, and we could just add computing questions to their platform, so that where they became our partner. So this is a sort of mixture of a research project and a delivery project all mixed up together. So these questions are all multiple choice questions, right? So I was a bit prejudiced against multiple choice questions, right? Isn't that just for babies? Actually, it turns out that multiple choice questions have a very strong educational pedigree and are extremely effective if used in the right way and if they're high quality questions, right? So one thing is you want the wrong answers, rather than just be random old wrong answers. Each wrong answer ideally embodies a misconception. So in this example, what's the lowest common multiple of 12 and 3? 3 is a divisor of 12 and 3, not a multiple. So the idea is that, and so is 4. So they're not just random wrong answers, they're wrong answers that could have a rationale for a student who sort of somehow got themselves backwards or upside down. So, and questions like this you can use in all sorts of ways. You can use them in quizzes to check progress. You can use a single question in class as a pedagogy. You can administer quizzes 3 weeks after you finish teaching that topic. There's a thing called spaced repetition that says if you get a student to revisit a topic that they have not studied for 3 weeks, it actually anchors the stuff in their memory more. It's all good. So multiple choice is fine. Formative assessment makes sense. Thank you, Jess. Probably going to go there. Are quizzes with questions even the right way to determine mastery? So Martin, Jess asked, are quizzes with questions the right way to determine mastery of a computing topic? Wouldn't demonstration be more effective? So I think that's an excellent question. If you want to say, how do you demonstrate mastery? Multiple choice questions of this kind are only one weapon in the armory. You need lots of weapons in the armory. Education is jolly complicated. This is just one thing. And it's specifically not meant to be summative, right? It's meant to be one way in which you might learn well, right? That's the goal. Okay. This all begs the question is, if we crowdsource the questions, how do we know if they're any good? I've been saying good, high quality multiple choice questions, good. Well, one way, of course, is we could use hand curation, but that's all labor intensive and even experts get this stuff wrong. So here's the big idea. Could you use data on hundreds of millions of answers to tens of thousands of questions given by millions of students? Could you take all of that data and answer questions like in the green boxes here? Things like, is this a good question? Does it discriminate between strong students and weak students? How hard is this question? Right, given the questions the students already answered, what should be the next question the student might try? These are all things that you might hope to get if you had enough data, right? And these days, the enough data thing is totally flavor of the month. So in fact, there's two flavors of the month here. So one is we're tackling this data in two different ways. One is Rasch analysis. So this is very well established, not new flavor of the month stuff, just standard educational practice. It's a statistical analysis of data on question answers. And pretty much it says, you can imagine this. If I told you that this was a high quality question and how hard all the high quality questions were on some linear scale, you could tell me how strong every student was, because you could just say which questions did they get right or wrong. But we don't know how hard every question is. If we knew how strong every student was, we could determine how hard all the questions were and which were high quality ones, because the low quality ones would not discriminate between strong students and weak students, and the high quality ones would at some point on the scale discriminate, right? And also you could tell where they would discriminate, and so you could tell how difficult each question was. So if you knew one half of this puzzle, you could figure out the other half, but we know neither half. So maybe we can just solve a simultaneous statistical equation and get best fit, and that's what Rasch analysis is. And so you can do this at scale. Yes, is there a link? So Brian asked, is there a link to Project Quantum? Yes, at the end I'm going to give you a link that indirectly links you to everything. Thanks, Brian, but search for, yes, I'll give you the link at the end. Okay. So this is that was magic number one. So that's kind of, as it were, using established technology but not applied. I believe Rasch analysis is usually applied to thousands of answers to a few questions in an exam. This is going to be at much bigger scale. But the second piece I just want to give you a sense about, because it's exciting to see computer science in the service of education, is to use machine learning. So here's the idea. You will know about the original Netflix challenge, in which various individuals offer their preferences of some, but not all, films. So here's an example. You say which ones you like, which ones you don't. And of course, most movies you haven't seen, you express no preference. And the task is, based on this very sparse matrix, fill in all the blanks. And that's the way recommender systems work. And they have been pretty effective in practice. Now, this is my colleague Cheng, who works on this kind of stuff and who is running the machine learning part of this project. If you just change the titles on the top of the columns from movies to questions and put in the boxes whether the student got the question right or wrong, and the blanks are the questions they haven't done, you can see it's really the same problem. Right? We could impute or guess the answers to all the questions they haven't done based on the answers that they have done, and of course what everybody else has said. The whole idea is to use the answers from some students to inform, to learn patterns that we might inform for others. So that would be amazing if we could do that, right? But if we could fill in this matrix based on, sort of recommender type technology, we could then answer questions like, how difficult is this question? Well, how difficult is this question? It's kind of like, you might say, a hard question, most students will get it wrong, right? So a completely filled in column, most students will get it wrong. How strong is the student? Look at the row. How many questions of all in the whole corpus do they get right? It's a sort of reflection of how strong they are. And we might ask the quality of the question. To what extent does knowing the answer to a single question, enable you to predict the rest of the, I should have said the rest of the column, or did I mean row here? Knowing the answer to a single question, maybe I mean column, yes, but predict the other. If you know the answer to a single question in a column, can you predict the other rows on the basis of that question? So how much does a question tell you about what the students will answer to other questions? So it's a sort of route to this kind of thing. So how does this magic work? So I've learned all this. I'm not a machine learning person at all, but I've had to learn. And here's what I've learned. So this is a sort of quick dive into autoencoders, and you'll be able to impress your friends. So if you're not already a machine learning person, if you are, then you can correct my mistakes. So the idea is that we're going to take information about a particular student, let's say student S. So that could be their age, their school, their eye color, their address, any metadata you have, probably sparse. You won't have much data about, you have some data about some students and not everything about everybody, but you'll also have all of the answers that they have given so far. You take all of that and you smush it into this neural network. The encoder just is a neural network, and it will spit out a vector of n floating point numbers. And the idea is those floating point numbers are called the student embedding. That's going to somehow characterize what we know about S, the student, with the idea that similar students will somehow encode to similar embeddings, nearby embeddings in this n-dimensional student embedding space. Then the decoder thing takes the embedding, the student embedding, and a particular question ID, and spits out the predicted answer from that student to that question. Okay, so it's called an autoencoder because the output, the output is the same as the input. We're trying to make the thing predict its own inputs, but under the artificial restriction that we've sort of squeezed down the bottleneck in the middle to the student embedding, because we're trying to make it generalize. We're trying to force it to say, well, similar students go to similar embeddings, and then if we get as we get a new student, we can determine their embedding based on what we know about them, and then we can predict their answers to all questions. So in this picture now, do you remember with Rasch analysis over here, students were kind of one-dimensional and questions were one-dimensional. They were just on a linear scale from 0 to 200. Now our students are n-dimensional, so that's much more likely to somehow accurately characterize the characteristics of a student in some mysterious machine learning-y way. So that's autoencoders. Now, what we're actually going to use is a variational autoencoder. So there, instead of n numbers, we're going to have n Gaussians, or more precisely, n mean standard deviation pairs, because a mean and a standard deviation will characterize a Gaussian. So you can think of that as, instead of n numbers, we're going to have n probability distributions of the numbers. So we can say for each student how confident we are about their about where they live on that particular dimension of the n-dimensional space. So this sort of starts to let us encode uncertainty, and then the decoder is going to spit out not the answer that whether they get it right or wrong, but the probability that they get it right or wrong, or in a multiple choice thing, the probability that they answer A, the probability they answer B, probability they answer C, and so forth. Now you can see if it's just yes, no, you can see that if this thing spits out 0 or 1, it's definitely going to say no, definitely going to say yes. Then the network believes it has high confidence about knowing the answer. If it says with probability 0.5 the students will get the answer correct, that's an indication of low confidence. So that's helpful because it means that this thing is going to give us some indication about how confident it is in the results. Now, the machine learning is complicated, and that even when neural networks say they're confident, that's not necessarily right? They might have had skewed data, all sorts of things might have gone wrong. This is not a magic bullet, but variational autoencoders are quite well established in all sorts of applications, and they seem to work quite well in this. So we tried it. Here's our first experiments we did last summer. Which we built this system and used it to fill in that whole matrix. And then we took 40 pairs of questions and we asked a human expert to say, of these pairs, which one was higher quality. On 80% of those 40, we agreed, our system agreed with the ordering that Craig said. So this is a really small sample. You can't draw any conclusion from this, but it was sort of encouraging. It suggested that we weren't completely up the spout. The other thing we tried to, so that was to do with quality of questions. Remember, that was one axis we were interested in. Another axis we're interested in is how hard this question is. So it's quite difficult to design experiments around this, but here's what we did. We took 13 collections of questions that we already had. This is the advantage of working with Eedi, right? They already had these collections. And we asked Craig to put these collections in a list ordered by difficulty. Now the collections themselves were typically, a year's program of study for a child. So he had a pretty good idea of which one was harder than which. And we then, not having that knowledge, just used machine learning to try to predict an ordering based on this the way of discovering difficulty that I described earlier. And it turned out that our prediction turned out to be much better correlated with the human experts ordering than a number of other competing approaches. There is a paper about this. As yet, sadly, unpublished, but it's on arXiv. So I would say we've taken sort of baby steps in this direction, and we've got sort of more going. What I really like about this project is that it's a real symbiosis between machine learning research, really, because that's a complicated, big space, real hot area. Lots of people at Microsoft Research are doing research in machine learning at the moment, but it's also very closely connected with delivery. We want this thing to be actually useful in practice for school teachers today. So I'm really excited about this because I love the idea of computer science in service of computing education. Okay, let's see. Last bit, just to finish. How can we help? How can we help? Zoom out again. I'm talking broadly about us as computing professionals, right? So I think we ought to want to help because this is our subject, right? We actually know this subject. This is what we're keen about. For teachers, I think it's a time of inspiration and opportunity, and also a time of anxiety and fear and stress, right? Because it is hard. You feel exposed when you are asked to teach something you really don't know very much about in the same kind of depth as you're used to. So there's really is a huge opportunity for us. And I think we can hope that somebody else will do something, but I would rather that we did something ourselves. So there's quite a lot going on in that in the UK. I guess a lot of you are based not in the UK, but I think still we should all individually and corporately roll up our sleeves. And I think this is a seminar within GitHub, within Microsoft, and I think there's quite a lot that we can do. We can do more together than we can individually. Yes, we can all help individually, but I think if we operate as groups, as work groups within our company, we'll be more effective because we can be, as partners for schools, we can be more reliable than a single individual can be. But a single individual can be keen and have time in one year, but not the next year. And that's not good for a school. So we can sustain over time. And it turns out the companies, Microsoft, GitHub, I'm sure, and in fact I know, and other companies more broadly, they're actually quite keen on this. They're quite supportive if you say this is what I'd like to do. But it doesn't happen. It doesn't happen unless we do something. We ourselves, we as individuals, have to lead, right? We can't just wait for somebody else to do it. So I'd like to encourage you to sooner start a group in your little bit of GitHub or Microsoft or anywhere else. Encourage each other. To sort of get those enthusiasms. I think of people together, instead of like in separate pieces, your little gobs of enthusiasm, the enthusiasms sort of go off into the ether and they get lost. When you're together, they sort of hit off each other and you get more, get an exothermic reaction going. And once you've got that, then you can start to form relationships with schools. You have to pick some actual schools and talk to them because you need to be grounded in reality. And to do that, you need to be somewhat proactive and be sort of humble as well, right? Because education is complicated and school teachers do know a lot about it. So it's no good parachuting in and say we know all the answers. We've got to really work in a sort of respectful and quite humble partnership with our school teachers, saying, how genuinely can I help? What do you need? And the only difficulty is they probably won't know. So you have to sort of be persistent enough to say, how can we work together to figure out what you need? Okay. The important thing is, don't just sit there, do something, do something. let me just finish here, right? So this is back with our children. I really want them to, this is not about some sort of political success. This is about enabling our children to be, empowered, informed, engaged, curious, playful, and yes, employed young people, and enthusiastic about the subject that we all hold dear. Here's a link that I promised you. The top one, despite the funny URL, is a page of links that I curate. So it has pointers to Project Quantum, to the Programme of Study, to the Royal Society reports, and lots more besides. The National Centre for Computing Education is that second link. So do take a look at these links for more information. And of course, I'd be thrilled to talk to any of you individually about this. But now we should stop and address questions. So Ugo, I'm going to go back to you and let you be in control of that. Hello, Ugo.
Hey there.
Yeah, there he is.
Thanks very much. Thanks very much, Simon. That was wonderfully inspiring. Thank you. A few questions already came in, and you addressed most of them.
Not the first one, though.
But it was exactly. So perhaps, so this is the question about at what age you would teach different sorts of abstraction. So, for example, polymorphism, object orientation. At what age do you bring in what concepts?
So this is a great question, because it's about pedagogy. It's about and concepts and conceptual structures, right? So I think I think the true answer is nobody really knows, because we don't have enough experience yet. But I believe that that children are perhaps more capable than we take them for. I don't think I want to teach polymorphism in primary school, but I think the program of study I referred to for this 2-page document does, certainly by the time you're at secondary school, aged 11 to 14, it specifically calls out in the control structures, loops and selection and sequencing and alternation. Polymorphism, I think, later, but then you need to sort of get into type system, object orientation. Well, there's a whole interesting thing. Some people would like to teach a lot, starting with objects and first principles. I don't know, but I think there's room for experimentation there. There's quite a lot of educational research about how to teach computer science at university level, not very much at school level. And there's a crying need. I think the way I think of it is, we've got we're spending £1 billion a year on school teachers to teach computing now, because they're all teaching this curriculum. And if you add them all up, it's a lot of money. We ought to be spending, $1 million or 10 million a year on researchers to help them to be even 20% more effective. Would be a fantastically good investment of £10 million. So I don't have a conclusive answer to your question, but I think it's the right kind of question to ask. And I think that the teachers and educational researchers do have a much sort of better characterized answer, and it's being but I think about elementary programming, I'm pretty sure that we can do a lot even at primary school. Like, lots of primary schools are doing Scratch programming and are doing, definitely writing loops, loops and control flow. They're doing all this at primary school, definitely today. I know. Now, it's not to say it's perfect progression. I don't know the perfect progression, but don't underestimate children, is perhaps what I'm saying. Okay, that was a long answer to a short question.
A new question came in from Brian Cardiff. When predicting a wrong answer, if the student is suggested to make first a learning task that would likely change the prediction, learning task taken is part of student metadata, is something. I'm not totally sure I understand the question, I'm afraid.
Brian can't talk, can he? So so I think maybe Brian's getting at something about his Brian Cardiff, about adaptive learning. So if a student gets a question wrong, an obvious question is, in an interactive system, you might hope that the system might then offer some some guidance about what's wrong, and then offer another question, maybe a little easier one, that would take you on a journey that would get you understanding the topic better. And so indeed, a very reasonable question to ask of a machine learning kind of system is, what question would maximize your information gain about students' knowledge in this topic? So a question about, if they get it wrong, what learning should you, what material should you offer them to help them learn better? That is, that's hard. That's a broader one than we're addressing, I think, right? So lots of ed tech platforms are addressing that kind of thing. They would like to say, our wonderful AI-driven platform will take you on a learning journey, will offer you all sorts of good information. And indeed, Eedi is building such a thing. But that's a lot more ambitious than in some ways, the project that I described, this quantum project, has quite a narrow focus. It's not solving the whole problem by any means, but it's a sufficiently constrained one that I think we might actually be able to make some progress. If you try to boil the ocean, I worry that you won't succeed. So I think, edtech platforms are trying to boil the ocean, because that's in the end the ocean wants to be boiled. But but this research project is more narrowly focused.
Very true.
That's what I wanted.
So far we've talked about computing as its own separate subject. So what about weaving computational thinking into other subjects, more computation and physics and maths, and perhaps we don't even need it separately.
So this is an important question, right? Because it's so let me first point out one danger. When we first, right back in 2008, people said to us, but you don't really need computing subject at all. We should just teach it as part of other subjects, shouldn't we? Right? It's ICT or computing across the curriculum. And there's something in that, because of course, computational thinking and informational thinking can and should infuse, physics and maths, and indeed perhaps history and geography too. Right? Thinking in a data science kind of way about geography really changes the lens a lot. But think about maths. If we said, let's not have maths as a separate subject, because we can just learn it when we need to solve simultaneous equations in a physics lesson, we'll learn to do that, right? It would never happen, because the physics teacher is interested in, how to figure out whether the magnet is doing the right thing. They're not really interested in simultaneous equations. That's a means to an end, right? So it would never happen. You need a sort of discrete subject to pay attention to the principles of that subject, and then infuse it in all of the others. So I'm very sure that we want to have computing as a and computer science in particular as a discrete subject, but not in a discrete silo any more than maths is in a discrete silo. So computing and maths are particularly symbiotic. I think of computing or computer science as mathematics made incarnate. That is, mathematics takes flesh, right? If you think about induction, right, some abstract mathematical idea, I think a for loop is like executable induction, right? In order to reason about the for loop, you do mathematical induction, but a for loop executes the induction. So I think of computing as the practical work of maths, really, and I would love to see maths and computer science taught as a sort of single integrated subject. Now, Bootstrap, which Leon mentioned, is a great program based in the USA out of Brown and Shuram and his colleagues. But I think it sort of teaches, I think it's sort of selling thing is it's mainly teaching maths, but through the medium of computing. I'd love to see even more integration and say we're teaching maths and computing both as foundational subjects in a sort of symbiotic way. But it's quite a challenge because nobody knows how to do that, and because it would take a teacher who had some sort of visceral, in their heart understanding about both mathematics and computer science, and there would be like hen's teeth. So I see that as being ambitious goal for the future rather than something we should do now. In fact, I think if we try to do that too early, I think we might screw up and end up with maths with a little genuflection to computing or computer science, and that would be that would lose the whole essence.
Totally. Jess Martin has another question. I'll read it out. I work at an online coding school, Lambda School, and we are experiencing the same struggle with writing our own valid formative assessments. It is a really hard problem. I do think an open source version of quizzing related to different languages and technologies could be incredibly useful, even for learners later in life. Our average student age is 32. What's the progress on open sourcing that question set?
Good question. I really think so. I want to open source not only the question set, but I want to what I would really like to do is to find a way to share the answers as well, because what I don't want is to take a corpus of 10,000 questions and fork it off somewhere else, and then the somewhere else gets lots of answers, but we don't get that data back, right? Because it's the data from all the people answering those questions we want to have in one place, so we can do all this learning out of it. So at the moment, to answer Jess directly, Jess, I hope that you will email me afterwards about this, because I'd love to talk to you. At the moment, the questions that they're all under Creative Commons license, but they're available currently in the form of completely free access through this Eedi platform, right? So, or the diagnostic question platform. And you can get to that, in an embedded way as well as a web service. We haven't yet got as far as let's take all of the questions, shrink wrap them in a box, and just toss them over the fence to somebody else, right? Because that would lose our connection with the data. But quite how to make the whole thing fly at scale in a way that's suitable for everybody else's platform, I haven't grappled with enough yet, and I'd love to talk to you about that. But that's my aspiration, right? Open source questions with all the data around it. Would be that's the goal. How do we achieve that? But it could be incredibly valuable. One repository of 10,000 questions with a billion answers is so much more valuable than 20 repositories of 1,000 questions with many fewer answers. Much.
Yes. Okay. Oh wow. Questions just keep coming in.
You want to pick one or?
Yeah, so let's take the one from Alex Taylor. So he's saying that a lot of the mathematical ideas that you need in computer science are actually only taught at really advanced stage. So logic, proofs, and you mentioned induction yourself. Actually, induction. Probably I encountered induction in university, not in school. So. We really would also have to change maths to teach the right concepts early enough.
Yeah, that's an interesting thought. I hadn't really thought very much about that. Yes. So at the moment, because I feel as if maths is like the big elephant in the room. It's got centuries of knowledge and baggage and thought about how to do it, and they're not going to look kindly on us upstarts telling them how to do it. But over time, I think as we gain credibility, I think they will pay attention. Indeed already are. So one interesting look at maths education that Alex might want to look at is called The Maths Fix. It's a book called The Maths Fix that Conrad Wolfram has just put out. Conrad and Stephen Wolfram are involved in, founded Wolfram, the company that do Mathematica and so forth. But Conrad's been deeply involved in maths education, and he has this book that says, and his thesis really is, we should not be teaching children long division, right? That's just teaching them to execute an algorithm. We have computers for that. Right?
Yes.
So his point is we should not teach maths as if computers did not exist. We should teach maths as if computers did exist and do exist, and that might reframe how we teach mathematics. Now, he's thinking of it primarily through the lens of we still want to teach maths, but we want to teach maths in a world in which Mathematica, for example, exists. I would also want to say we want to teach maths and computer in symbiosis with each other, and that might indeed influence about which bits of maths we teach first, as Alex suggests. I haven't really thought of that very much, but it must so it's entirely plausible.
Okay, we're up against time. Thanks everyone for attending. Thanks for the great questions. Hopefully we can continue online. I'll just close by paraphrasing the last comment posted by Brian Abbott. Computer science is mathematics incarnate. I love Simon. Thank you for, he said, thank you for the gift that you gave to all of us in Haskell. Simon, thanks very much for yet another wonderfully inspiring talk.
Great, it's a pleasure. Thank you. Thanks for the opportunity. Right, cheers.